In this video, we will be looking at significant figures in calculations and measurements. First thing we have to think about in significant figures is even though we're dealing with numbers, these numbers are supposed to reflect what we know about a physical object or something in our physical world. The first thing we really want to be aware of is that all measurements contain some level of uncertainty. It doesn't matter if you're measuring something with a ruler, whether you're measuring something on a simple balance, a complicated balance. Any measurement you take, whether it's done by an instrument or by hand, has some degree of uncertainty in it. And depending upon what instrument or what measuring device you use in order to make that measurement, that's going to affect how uncertain that measurement is, or how much certainty there is versus uncertainty. A lot of times when we do a measurement, there's an estimated digit. A digit that's estimated is called uncertain. We're not really sure of that based upon what that instrument can provide for us. That's where the certainty ends and an estimation begins. And that's usually the last recorded digit. The two balances in the picture below do a good job of kind of representing how we take measurements and what significant figures really tell us. So these two balances have different levels of certainty and uncertainty. The one on the left is a relatively simple balance. It can estimate down to the hundredths place. Its certainty runs out in the tenths place. Meanwhile, the balance on the right, we see that we have certainty all the way down to the thousandths place, but now we're uncertain at the 10,000ths place. So there's a different degree of certainty in the measurements if we were to weigh something on each one of these balances. And that's what we want to think about. Imagine putting the exact same object on each one of these balances. Now, regardless of which balance you put it on, the object didn't change. But the information we're getting back is going to be a little bit different based upon what device we are trying to measure that solid object on. So that's really important when we start thinking about going beyond numbers, because sometimes we can get lost in the rules for significant figures and we lose sight of what's actually physically happening. We're trying to tell a story about what that measurement is, what that measurement is actually doing. So significant figures tell us the level of uncertainty in a measurement. They can be used to determine what instrument was used to conduct that measurement. If we look back at the previous slide and you think about those two balances, well, based upon you would report that mass to somebody else, they would know kind of what level of scale or what level of balance you use to make that measurement. Anytime we're taking a measurement, we're allowed one place, one digit of estimation. So our rules for counting significant figures, remember, all these kind of play back to this idea of we're getting some physical knowledge about that measurement that we took. So the first rule is pretty straightforward, and that's anytime you have a non-zero digit, so non-zero digits are those 1 through 9, those are always going to be significant. There's no exceptions to that. Those are always going to be significant. So for an example, if we look at the number 213.5, those are all non-zero digits. So this would have 4 significant figures in it. All of those would count as significant. In the number 1.54, all of these are non-zero digits. So we would have 3 significant figures in that number. It gets a little bit more complicated and potentially confusing when you start getting into zeros. And that's because there's different types of zeros. So you have to identify what type you're dealing with. And they all kind of have little slang, catchy names that go along with them that help you realize what type of zero you have. The first we call leading zeros. So these leading zeros, kind of just what the name is implying, are zeros before the first non-zero number. These leading zeros are not significant. Sometimes they go by the name placeholder zeros. So here we have two examples of looking at some leading zeros. And the first one, 0.0023. We look at these zeros. All of these zeros appear before the first non-zero digit. That means those zeros are not significant. So the zeros aren't significant, but the 2 and the 3 are. That's where we're going to get our two significant figures from. In the number 0.000000675, all of those zeros are leading zeros. Those are not going to be significant, so our only significant figures in this would be the 6, the 7, and the 5, and we would wind up with 3 significant figures. Kind of almost the exact opposite of the leading zeros are the trailing zeros. These are zeros that appear to the right of the last non-zero digit and it's a very important and, to the right of the decimal place. So both things have to be true. They have to be to the right of the last non-zero digit and to the right of the decimal place. These end up being significant. And we can kind of think that they're going to be significant because they're telling a different story. So let's look at some examples of some trailing zeros. The first, 19.3400. Well, we know the 1, the 9, the 3, and the 4 are definitely significant because they're non-zero. But we look at these zeros, these are trailing zeros. They're to the right of the last non-zero digit and to the right of the decimal place. Those are going to be significant as well for 6 significant figures. Now, you may be looking at this and say, well, why do those zeros even matter? Because they don't change the numerical value of the number. Well, you'd be right, they don't. But what they do is they tell you what level the measurement was at, where your uncertainty happened. If you didn't have these zeros, well, then your estimation was here at the hundredths place with the 4. Here, you're showing that your measurement was much more certain than that. Your measurement told you that I could estimate all the way down here to the 10,000ths place, and I already had certainty at the thousandths place. So even though those trailing zeros don't change the numerical value of the number any, they're very important because they're telling you something about that measurement. What level did you know that at? If we look at another example, 0.00000003200, here I have a mixture of some leading zeros. All the front zeros are leading zeros. Those are not going to be significant. We know the 3 and the 2 will be significant. These two zeros are trailing zeros, so I'm going to have a total of 4 significant figures in that digit. Another type of zero is a captured zero. A captured zero are ones that are between two other significant figures. So these captured zeros kind of lie in between. They're captured by other significant figures. And if you have a significant figure to the left and to the right, well, it'd probably be pretty safe to assume that these are going to be significant as well. So here, let's look at some examples of some captured zeros. So 2304.1, well, we know the 2, the 3, the 4, and the 1 are all significant. This 0 is captured between the 3 and the 4. So being it's captured between the 3 and the 4, that's going to be significant. All of these are going to be significant figures. It doesn't matter where in the decimal place, to the left or right, these captured zeros appear. Our next example, 13.6009. Well, the 1, the 3, and the 6 are definitely significant. They're non-zero. Same with the 9. Here, I can have more than one captured zero. Here I have 2 captured zeros. Well, they're between the 6 and 9. Those must be significant. All of these are significant. We'd wind up with 6 significant figures. the 1900.000, well, we know the 1 and the 9 are significant. We actually don't know anything about these zeros that are kind of above the green here. Those first two zeros we don't know anything about yet, but what we do know is that the zeros to the right of the decimal place are going to be trailing zeros. Why? These three zeros to the right of the decimal place are to the right of the decimal place and to the right of the last non-zero number. So those are going to be trailing zeros. Those three at the end are significant. Now that those are significant, these two zeros, these first two zeros that we found, that we saw in the number, these are now going to be captured zeros and are going to be significant as well. There's another type of zero, and this is a zero we really want to avoid because it can be very confusing how to deal with this, and these are ambiguous zeros. And just like the name applies, they're very ambiguous. It's tough to tell what is meant by that zero. These are zeros that sometimes appear in a large whole number. It's difficult to tell if these are going to be significant or not. An example is 2400. Are these zeros significant or not? Or maybe are some of these maybe significant while the other ones are not? It's very, very tough to tell. So being it's so tough to tell, we need to have a way of avoiding this while still being able to represent these large whole numbers that may contain zeros. So to avoid writing these ambiguous zeros, when you have this large whole number where it's confusing, it's best to rewrite the number using scientific notation to be clear what the zeros are. Let's kind of look at that. 24,000, well, how can I write that such that it was really clear that I don't want the zeros to be significant, or I want the first one to be, or the second one, or the third one? It's really tough, but there is a way. The way to do that is to change this using scientific notation. If I change this to scientific notation, I can write it such a way that these ambiguous zeros I can clearly put as a different type of zero. And let's see that. If I don't want those zeros to be significant, I could rewrite this in scientific notation to be 2.4 times 10 to the fourth. I'm chopping those zeros out, and that's showing very clearly two significant figures now. Now those zeros weren't significant. If I need the first zero to be significant, but not the second two, if I rewrite that in scientific notation as 2.40 times 10 to the fourth, well, I'm showing that first zero as significant. I get my three significant figures there. If I need to show four significant figures, or that the first two zeros are significant but the last one is not, I can rewrite it in a way that shows that. 2.400 times 10 to the fourth. I can clearly see those four significant figures. What I'm doing with these ambiguous zeros going through the scientific notation is if I don't want them to be significant, I leave them out of the scientific notation. If I need them to be significant, when I rewrite the number in scientific notation, those ambiguous zeros are now becoming trailing zeros, which are perfectly clear to the reader that, hey, these are meant to be significant. If I need all of them to be significant, I can rewrite that way. 2.400 times 10 to the fourth, I'd get the five significant figures out of here. Now here's another case where when you look at this, the numerical value of all of these numbers is identical. Mathematically, in a pure mathematical sense, those are all exactly the same. All of these numbers. It's still 24,000, a pure abstract mathematical sense. But how I choose to represent that number can display some physical meaning to what that number really represents. And that's why significant figures are important. So we can use scientific notation to display the correct number of significant figures when we're dealing with some of these ambiguous zeros. There's some other type of numbers. These are called exact numbers. An exact number does not come from a measurement. And just kind of what their name is implying, they are known exactly. If you know something exactly, there's zero uncertainty. Since there's no uncertainty, these numbers would have an infinite number of significant figures regardless of how you write them. Okay? So you have to understand when you're working with numbers where that number is coming from. There's two types of exact numbers. The first type of exact numbers are counting numbers. These are things you can physically count. Even though you may look at it and say physically counting is a form of a measurement, it's generally assumed that if you physically count things, there's no uncertainty to it. So when we say 6 pencils on a table or a desk in front of us, that 6 came from a counting type number. It was a counting number. We physically were able to count those 6 pencils. We're not looking at one significant figure here for the 6. It really has an infinite. We don't write 6.000000000 because that gets very cumbersome. Instead, we recognize, hey, that was a counting number. That's going to have an infinite number of significant figures. Same thing with 14 sheets of paper. You have 14 sheets of paper on your desk in front of you. Well, that's not 2 significant figures from the 1 and the 4. You physically counted out those 14 sheets of paper. You counted out those 14 sheets of paper. There's no uncertainty to that. This would really have an infinite number of significant figures to it. Your second type of exact number are definitions. And if you have a definition, you're going to define that relationship to be exactly true. So that definition is an exact definition. And we use these all the time. 12 inches equals 1 foot. Well, the 12 inches isn't 2 significant figures, and the 1 foot isn't 1 significant figure. This is exactly 12 inches equals exactly 1 foot. That's the definition. We understand that that's exact. That didn't come from a measurement. That came from an exact definition. Those would have an infinite number of significant figures. Other ones we could talk about, 1,000 grams equals a kilogram. Again, that's a definition. Infinite number of significant figures. 7 days in a week. Not 1 significant figure from the 7 days or 1 significant figure from the week. An infinite number of significant figures. 4 cups in a quart. Again, exact number because it's coming from a definition. A lot of times we're not just measuring something and then it goes away. We're doing something with that measurement. So there's rules for dealing with significant figures, especially in terms of the rounding. Basically, what you're doing is at the end of a calculation, you're dropping insignificant digits, things that don't have any physical meaning. This is only at the end of calculations. And this really involves kind of the weakest link principle. And you may have heard of this principle in reference to a chain. You maybe heard the old saying, a chain is only as strong as its weakest link. And what that means is, no matter how strong the other links in the chain are, the overall strength of that chain is based upon whatever the weakest link in there is. That's where it's going to break. Even if the other links can hold a lot more, it just doesn't matter because it's going to break at the weakest link. That same idea, that same principle applies to our calculations and our significant figures. The number of significant figures in the final result cannot be greater than the weakest link used in the calculation. And that kind of makes sense. Your end result can't be any better than the numbers that went into it. It just can't happen because you already have a lot of uncertainty in an initial number. You can't all of a sudden get less uncertainty out of your final answer. So the actual rule depends upon the exact mathematical operation. Let's have a look at a couple examples of that. Multiplication division is the biggest one. You end up following this rule all the time. number of significant figures in the result is the same as the number in the least precise measurement used in the calculation. So here we're looking at 6.38 times 2.0. Well, the mathematical answer to that is 12.76. But when we're dealing with physical objects, we have to represent that certainty in that measurement. Well, here, 6.38 had 3 significant figures. 2.0 only had 2 significant figures. So that means we need to round our final answer to those 2 places. So I need to round here at the ones place. So that's why I'm rounding up to 13 to represent the 2 significant figures. Works same way with division. 16.84 divided by 2.54. Well, the 16.84, that's 4 significant figures. The 2.54, 3 significant figures. When you just throw that into your calculator, you get the 6.6299. That's the mathematical answer, but that doesn't have a physical reality. The physical reality here is I only know up to 3 significant figures, so I need to round to 3 places. 1, 2, 3, that would be in the hundredths place here, so rounding to the hundredths place, I'd go 6.63. My 3 significant figures would match the least precise measurement I use in that calculation. If you were doing a whole string of 5 or 6 multiplications or divisions in a row, you would just look for your least precise measurement that was used in that and then round your final value to that. Addition and subtraction works with the same general idea, a little bit different mathematical rule. Here, this weakest link idea is that the number of significant figures in the result depends upon the number of decimal places in the least accurate measurement. So here, 6.8 plus 11.934. What that means is 6.8, I'm looking at the 10th spot. 11.934, I'm at the thousandths place. The 10th place is less precise, less accurate. Therefore, my final answer, I only know down to the 10th place. That's where I have to round things at. Same thing for subtraction, 37.657 minus 6.21. Well, the 35.557, that is the mathematical answer, but that doesn't represent the physical reality very well. So here, I'm looking at my decimal places again, because that's how we work with addition and subtraction. The 37.657 is at the thousandths place. The 2.1 is at the 10th place. That means I need to round at the 10th place. So my final answer, I need to round at that 10th place, and that's going to give me my final value. So multiplication and division, we're looking at least number of significant figures. Addition and subtraction, least number of decimal places.